Thank you.
Yeah. I hope all the participants are doing well and are excited for this technical session. To introduce myself, I am a doctor. I am Dr. Kedar Batwardhan. Working with Chem Club for on various training sessions on high seas, steady state, dynamic, the heat exchanger, fire heater part. And today we will discuss one of the most important and practical areas in process engineering, which is a dynamic simulation and the transition from the steady state model to a dynamic model. So in many industries, in refineries, petrochemical, fertilizer, LNG, hydrogen plant, you name whatever, so engineers generally begin their study with the steady state simulation. So the purpose of steady state simulation is pretty clear to everyone. Basically, develop a heat and mass balance, identify the design cases, and then basically you design the plant based on the worst case scenario or keeping your design margins and all. But when it comes to dynamic, the steady state is the wish list, I will say, and for a engineer, process or operation engineer. But however, actual plant doesn't actually operate, in a truly steady state. Always there is some fluctuation that may happen. At least there will be a startup shutdown. There will be change in the feed, change in the some pressure variables and other things. Not if it is not within the plan, at least it will be at the planned battery limit. So that actually is a case study basically for a dynamic simulation. So plan the so the the changes that we normally encounter are like feed composition changes, flow fluctuations, compressor trips. If especially if you are having a pump or a compressor, so they are actually their performance keep on varying. Valve failures, startup shutdowns, emergency depressurization scenarios, control interactions. So all these are actually are the case studies for the dynamic simulation. So the dynamic simulation can help you basically to understand what is the science that is happening behind it, and what is the impact of all these variable change in the conditions and on the performance of the plant. And ultimately under those conditions, the criteria is basically to keep the plant in a safe operation. Whether you want to go for a shutdown, that is also okay, but then the safe operation under that scenario. So that is the main purpose. And especially if you are having a normal operation, then again also, so dynamic simulation can help you to see what are the control. You can actually replicate what is there, what are the control process control that are there in the plant. And you can see whether at the design stage you can see if you can you can fine tune basically, rather than running on an actual plant. So that is one important thing that the dynamic simulation can help you. uh, so in today's webinar, we will help you to understand what dynamic simulation really means, how it differs from steady state simulation. People consider, once you know steady state, that the dynamic is only a a differential of time. But that is not how the software works. So we will tell you how what are the differences between a steady state and a dynamic simulation. The key concept used in the Aspen HYSYS dynamic. We are talking about the HYSYS site in this particular case. Then there is a pressure flow relationship. We will come to know once we will go to that particular thing, why pressure and flow relationship is important here. Pressure nodes and resistance equations. Again, it's a new thing to be learned under dynamic simulation. Equipment sizing requirement. Yeah, it is there in the steady state as well as in the dynamic, but dynamic it is more important. Dynamic specifications. Common transition methodology from steady state to dynamic. So we are going to cover the basic steps that needs to be taken when you want to convert your steady state simulation into a dynamic simulation, and it remains the basically same, whether you whatever may be the complexity of of the process. The basic steps are going to remain the same, and that is what we are going to cover in today's the demo. So this session is designed specifically for process engineers, simulation engineers, control system engineers. We don't have so many names in India specifically, but you may take one of these roles in your organization, and then safety engineers, because ultimately when the control system fails, finally it is how we can operate the plant in a safe way. So that is one of the outcome of the dynamic simulation. And then the graduate engineers entering into, who want to wish who are wishing to create their career, and they are the right candidate to go for this webinar. I encourage everyone to think practically during the session. Try to visualize how real plant behave during transient operation. And so with this, let us begin. Um, so. Uh, so this, I think we have, one of the things, like, imagine a chemical plant running smoothly at normal condition. Suddenly you will say, that the feed flow increases, a pump trips, or a wall closes unexpectedly. So all these are the basically the scenarios where you want to see how the plant will respond to that. That is what we are going to cover. Now, real system, real plant disturbance is, so that we have already talked about. Uh, so, the so what happens next? So what we have covered here are different scenarios. You can add as many scenarios as you can think. So those actually scenarios actually can cause a disturbance in the plant performance. So what happens next? How the plant, does not instantly jump to a new stable condition. So instead, you can have a pressure begins changing gradually. Temperature starts drifting. So all these, it follows basically a transient path. It doesn't go now. This is my new condition. So when you are carrying out your simulation under steady state, so what you do is you now say though. So this is second scenario where the plant is operating now under new condition, and this is how the HMB will look like. But it doesn't happen that way in the plant. So it actually follows a set of procedures or steps to come to that. So pressure will begins changing gradually. Temperature starts drifting. Levels in the separators or in the vessels, they will start increasing or decreasing based on the scenario. Controllers start reacting. Ball starts moving. Safety system may activate. So all these things keep on happening based on how through which path the plant is going through, and then ultimately it will reach another state. So all these scenarios are complex in nature, and they have a very high interdependability. So that is why it is very difficult to imagine. And when it happens in such a quick way. So you don't get a time also to take any actions sometimes. So it is always better to do all these, replicate that on a computer, which will give you a fair bit of idea, and you can see where you are shortfall for the process control, and you can take corrective measures. So this entire process happen within very quick time. So I have seen in plants, it has happened. There were, I think, four or five interacting scenarios, and before anybody can understand, the plant has tripped. So it's a very fast process. So to understand this on a real plant is the best experience. But now studying same thing on a platform is a very cheap option, and it actually can help you to get into very basic fundamentals, because these simulation softwares are based on the basic thermodynamics, basic mass transfer, heat transfer principles. So it can give you a more idea how and why that thing has happened. So yeah uh, so uh, so let us formally define now what is dynamic simulation. Okay, so that dynamic simulation is a modeling technique used to study how process variable change with time during transient conditions. Unlike the steady state simulation, which calculates only the final equilibrium operating condition, dynamic simulation continuously calculates what it calculates: pressure versus time, temperature versus time, flow versus time, level versus time, composition versus time. So these are the main process parameters normally a process engineer is looking at in even in at the plant. So these allow engineer to observe the complete process response during disturbances. So dynamic simulation become extremely useful in scenario such as if I can name some of these scenario: the plant startup, shutdown, compressor trip. So compressor trip is I think so if you go to any software for that matter. So compressor has been given the utmost importance because that unit itself is a very costly item, and it's a very dynamic also at the same time. So there are separate modules that are available, which actually take care of these compressor trip studies and other things. Emergency depressurization, flare load estimation, control valve tuning, PID controller testing, safety interlock verification, operator training simulator. That is what just Jatin has mentioned, OTS. So this is one of the it's again a dynamic simulation can actually can become a platform for OTS, like the operator training simulators. So one major advantage is that the engineers can test abnormal scenario safely in the virtual environment, because we are not experimenting with the and nobody will let you touch the things there in the operation. So only the experienced people who are sitting on the will only be handling such situation, while the new people or who have not gain any experience will be asked to sit back and see how it is observed, and then over a period of time you will get. But this software training, the dynamic simulation software can actually help the engineer to see all these study at a much cheaper cost. So that is what the uh, main advantage. So industry use dynamic simulation extensively, improve process safety, reduce operational risk, optimize control strategies, validate shutdown philosophy, train operators, improve plant reliability. So these are the dynamic simulation is sometimes mandatory in the projects in the Middle East. So in Middle East, our operators, if you compare Indian operators versus Middle East operators, the Indian operators are much more, I'll say, they have a risk appetite that has been given to them by their management. While in the Middle East, they normally follow all these sequence where the engineering contractor is asked to give the training of the individual packages, etc., etc., and he has to be the engineer has to also give a dynamic simulation training to the operators for various scenarios that the plant can see. So today, that awareness I think is also increasing in India also, and that is why we have kept this webinar just to make understand of the importance, and how we can do that as a preliminary course. So today some commonly used software platforms are Aspen HYSYS, Aspen Plus. So HYSYS is normally used for refineries, while Plus is normally used for chemicals and petrochemicals. HYSYS again for the gas processing. Um, so uh, so Next slide. So this is what the coverage of dynamic simulation. So when we say dynamic simulation, what are we? What all is covered? So, what is dynamic simulation? So, that is what we are going to cover. Steady state versus dynamic simulation, yes, that we are going to touch. Basic concept, so all these are basically a stepwise, training. So, we are going to cover the first, second, and the third topic in this. and the process control and other things. So process control has PNID controllers, controller valves, flow control, pressure controller, temperature controller, level controller, etc., etc. So all these are available under HYSYS, under dynamic simulation. And it can be it requires a little it's an maybe I'll say the level 2 type of training, where you will go into the process control, get more details of that, get PNIDs, and start making what the actual plant is going to see. So that is the second level of where we go into simulation. Then the logic, interlock, alarms, etc. So again, that is an outcome basically of these process control loops that is included in the dynamic simulation. Compressor and anti-surge control, again, as I said, this is a very very important thing, and I think dynamic simulation got more I'll think I'll say the attention, major attention, because of this compressor anti-surge control only. So there are separate modules within the dynamic simulation. So that is another, I'll say it's not level 3, but it's a level 2, but part B. So you have process controls, and then you are having a compressor anti-surge controls. Then we are having an advanced process control, so APC, which is again, it's a so APC basically sit upon the normal process control, and it takes an overall charge of how the process can be optimized also. Not just the safe operation, but it can be optimized from the energy point of view and from the operating cost point of view, how we can operate that plant. So that is an again an advanced, very advanced level of thing, study that is done. And then typical instrument that are modular, flow transmitter, all that whatever can be are there in the plant, flow transmitter, pressure transmitter, temperature level transmitter, control valves, etc. All that can be incorporated in the dynamic simulation. Then apart from Aspen, which I have named earlier, so we are having an Honeywell, which is more or less similar software as that of Aspen HYSYS. We have as Aviva Dynesim. Then there are a couple of others like Olga, which are very specific to flow transition, and AFT impulse, which is again very specific to the flow transition, flow transfer. So these are basically Olga and AFT. They are mainly used in the offshore platform, where you have a transient slug that may come, and a slug catcher, that is the first equipment that it sees how to size that slug catcher. So that is done mostly by Olga or AFT. Yeah. So the next is transition from steady state to dynamic. We will move into one of the most important now technical session. So till now we have given you some background, why it is important, and how what are the features of dynamic simulation and other things. We'll go now one step deeper into how the dynamic solver works. So the dynamic solver in Aspen HYSYS is fundamentally different from the steady state solver. So this is a very important concept that needs to be kept in mind, because in steady state simulation, the calculations are usually sequential. So there are two methods. If you have used HYSYS earlier and done the steady state simulation, so if you start with the HYSYS, it will do these calculations. So once you define your first stream, and downwards, if you add a separator, so automatically the separator is solved, and it will automatically tell you what is the vapor phase composition and liquid phase composition, etc., etc. So that is called a sequential sequential model, sequential SM mode. So sequential modular mode, sequential mode. So basically, it will start calculating from the left side. As you keep on adding your unit operation, it will start calculating it and then ultimately you will finish your entire flow sheet. So one unit operation solves after another. So that is the sequential way what you calculate. There is no accumulation. So this is a very important thing. So so when you are doing the simulation, steady state simulation, the equipment volumes are not at all important. So what your objective is to see what are the feed pressure, temperature, flow, composition after that unit operation. So you are basically looking at the how the what is expected basically from that unit operation. So so there is no accumulation, because that accumulation terms comes only when the volume is there. So the steady state will give you basically what is expected from that equipment, and to get that performance, how the equipment should look like. Basically, what is the size, what are the heat transfer area, if it is an heat exchanger, etc., etc. So, so there is no accumulation considered. Whatever is being coming in, it should come out. So you say, say if you are having a distillation column, which is a complex unit operation. So feed in is equal to whatever number of feeds that are going out of that column. They should match, and finally the in and out should equal to zero. So that means there is no accumulation. While as in dynamic, there the and also the time is not considered. So this is the steady state operation where it is going to happen. If you are putting this much amount, this is going to come out. But in dynamics, the entire flow sheet behaves simultaneously. So, the so it is again now it is far different than the steady state. Pressure and flow interact continuously. The material accumulation occurs, and time dependency becomes important. So these are the four things which in steady state which were not considered. Now they are part of the dynamic. So dynamic solver treats the flow sheet as a boundary value problem. So you have to define, like if you have you have participated in any HAZOP. In HAZOP, you normally mark, your nodes. So node one, node two, node three, and then you discuss that this is my node. So I am not now discussing what is happening beyond that node. And what is going to happen after this node. So I am only talking about the nodes and considering some battery limits. Okay, so fiction battery limits. So, so similarly in dynamics also, so you study these nodes, you develop the dynamic. It need not be a complete simulation, plant-wide simulation that you will be studying. Otherwise, you will be lost. So dynamic simulations are very specific and are with a very specific purpose. So you analyze that, you replicate that node with all minor details that are there, and then you study the transient behavior within that particular boundary limit. So that is why the boundary conditions must be defined properly. Pressure and flow specifications are extremely important. So the three concepts that govern the dynamic simulation are pressure flow specification. So boundary streams must have proper pressure or flow definitions. We will come to that in more detail when we will take one example at the end. But just keep that in mind that pressure and flow specification are very important at the battery limit of the at the boundary limit of the whatever system that we have considered. Then second is the resistance equations. So resistance are basically nothing but it's a unit operation which is causing, or for that matter any equipment or unit operation or any even a pipe. So so these particular equipment or unit operation is providing basically a resistance in the sense there is an, like the resistance what we normally get is that the electricity. So when there is an there is a resistance, then that is why the current flows. The same concept is there in the dynamic. So you create a resistance, and that resistance actually create a pressure drop. Now this pressure drop is the reason why the flow occurs. So this is a very important concept in dynamic simulation. So whenever there is a pressure drop, the flow will transfer from high pressure to the low pressure, and higher the amount of the pressure drop, higher will be the amount of flow that will occur. So that is not the concept in the steady state, because in steady state you may go away with your simulation, considering a zero pressure drop in your separator, zero pressure drop in your wall, zero pressure drop in your heat exchanger. It doesn't matter, because these are only to give you the material and energy balance. While as in dynamic simulation, the resistances are important. So resistance equation are can be given in the form of walls, heat exchangers, pumps, compressors, etc. Then there are pressure nodes. So they represent the location where accumulation occurs. Say for example, like separator, you are having a drum, column, tanks, basically some static equipment which are having an appreciable amount of hold up volume, and then they are considered to be the pressure nodes. So a very important industry rule is the no pressure drop means no flow. Flow always occur because of the pressure difference, and this is the most common mistake engineer make during transition to dynamic. So this has to be always kept in mind, that when it comes to dynamic, there should be some pressure drop and there should be some volume provided to all those unit operations or the equipment which are there within that node. Uh, so, uh, so this picture actually can give you a more detailed information about this. Um, so the central idea is flow depends on the pressure difference. So if you are having a pressure drop, so the pressure drop will be in the wall, in the second wall, in the third wall, and then because there is a gap of pressure that we have already specified at the battery limit of this node. So the pressure is higher on this side, while because of the pressure drop that is observed by these vessel, these walls, the pressure at the on the vapor side or on the liquid side will decide how much flow that can occur through these streams. So that is the idea. The equation that you can see is flow is a function of pressure drop, and the pressure at pressure node, the change in the pressure with respect to time is a function of the volume, the temperature, and the flow changes. Okay, so this is the pressure node which I was talking about in the previous slide, and these are the resistance equations, and these are the battery limits. Pressure P spec, which is a specification which has to be provided at the battery limit of this node. The resistance equations which is created in the wall, it can be exchanger as well, or some other equipment as well. And then there are pressure nodes, which is just basically having a liquid, basically a volume, appreciable volume. So that is called as a pressure node. So this is a very simple example which tells you all the features which we have discussed earlier. So so just to give an example, so outflow, so outlet walls, say for example, if we close this wall, so what will happen? Because now, the outflow will decrease. Okay, the material will accumulate, the pressure will rise, and controller will respond. Okay, so there, if we are having any controller in this, so it will respond to that. So that is how the system will work. And in dynamics, when you will develop a model, so it will also actually show the same analysis as that you can see in the plant. So coming to dynamic solver execution, let us understand how Aspen HYSYS dynamic performance calculations internally. The software continuously solves pressure flow equation, material balance, energy balance, control equations, flash calculations. So these are the calculations. So the material energy balance and flash calculations are done at the steady state level as well. The only two additions are the pressure flow equations and the control equation. So so differential calculations occur at different frequencies. So pressure flow calculations are solved at every time step because they are highly dynamic. While the material balance, energy balance, and flash calculations are basically are counter check. So once a particular loop is being calculated, so it will be solved only once to check whether the material energy balance and flash calculations are basically they are conservative equations. Composition and flash calculation may be solved less frequently to reduce the computational load. The integrator controls the time step size, numerical stability, and solution speed. So when you we will show you what do you mean by integrated integrator. So integrated is nothing but when you are solving these the dynamic simulation calculations or equations. So the T is basically is it's a with respect to T, right? So it's a differential equation with respect to T. So when you are having the so integration integrator basically is the one which actually gives a tool to you to basically to check whether what is the time step you want, the numerical stability and the solution speed. So that that is a control given to a user, so who can actually manipulate on that to get more correct results and more I'll say uh, more meaningful results. So choosing proper integrator setting is very important for stable simulation performance. Too large time steps can miss important dynamics and it can cause instability, and too small steps can increase the computational time. So these are the two the extremes, and then practically you have to base on what is the dynamic of that particular system. Say if you are having the compressors and pumps, etc., so the dynamic becomes more, I'll say, the frequency has to be increased. So because the conditions, the pressure, temperature conditions, etc., will vary very fast with respect to time. Whereas if you are having a system like what we have discussed here, so here you will see more of static equipments are there. So the response to the system is also very slow. So then it is up to you. So there are some default setting in the integrator how to that is provided by HYSYS. But you can always, as a user, you can modify those. So okay. So dynamic solver procedure is distributed. There are either it's a distributed system or a lump system. So let us discuss these two important modeling philosophy. So in distributed system, the properties vary across space and time. Temperature gradient exists, composition gradients also exist, and pressure varies continuously. So these systems require partial differential equation and are typically solved using CFD tools. Our CFD tools are are computationally intensive. So dynamic process simulator like HYSYS usually use the lump parameter approach. So distributed system are normally when basically they are partial in the sense what happens is whenever you are having two parameters affecting one time and they are interdependent. So in that particular case, you normally go with a partial differential equation. While as when you are having only one system and one with that needs to be changed with respect to time, so that becomes a ordinary differential equation. So partial differential equation normally are solved in two spatial coordinates, and while as lump parameter system they are actually are solved in single direction. So basically x with respect to time. So that is how the lump systems are, and so it requires a little considerably smaller time, and also you can get the result much faster, and then coupled with all your material balance, energy balance, actually it can give you a better picture, even with the dynamic simulation, process simulation. Uh, so in lump system, what happens is the special variations are ignored. Properties are assumed uniform inside the equipment, and ordinary differential equations are solved. So that is what reduces your computational time, and it can give you. But it's basically an approximation. While as if you go with the CFD, it will try to replicate what exactly happening at a very a very micro level, and you can actually get more insight, but at the same time, the cost, etc., and the time to run and other things are also very high. So this is one, I think, one of the uh, simplified version. That is why it becomes practical even for the entire refinery unit, for that matter, LNG trains, compressor networks, utility systems. So whenever you are handling a big process schemes, it is better to go with the lump system, while as distributed system can actually help you to go to much more detail, but then you cannot cover the entire system there. Now, how to do the setting up of a dynamic model? In dynamic model, the process simulation requires additional specification in order to calculate um, three things. One is the dynamic PF specifications on battery limit, then pressure nodes equation in location where for accumulation is made, and the resistance. So we have already we have uh, uh, we have already discussed this point. So in say for a simple system or a simple node like this, so you can see here that there are pressure specification that needs to be made at all the endpoints. Then we have to have a resistance. So the pressure drop in the systems are caused by either by pipe segment, or you can put a wall here, so that will cause a flow to occur. And then there are the separators, even the resistance is provided by the heat exchanger here in the heater, and then you are having a tower and a separator which acts like a pressure node equations for the accumulation. So uh, then the next step is basically the sizing of the equipment. So as I said, that there are three things that are very important. One is that again you have to have a pressure drop. So that is important thing. But apart from that, the volume is also important. Now, why volume is important? Because the volume decides what is the effect of how the system is going to respond for that change. So if you are having a very large volume, say for example, I'll just give one example of a PSA. So PSA in a hydrogen generation unit, the off gas that is generated from the PSA, which is the pressure swing adsorption. So the pressure swing adsorption is a semi-batch process. So the off gas is generated in a pulse manner. So those pulse are basically are like a a dynamic simulation. You can consider there is a a pulse that the flow is coming for a very few seconds of a time, and then again there will not be any flow, again there is a flow. So it's a like a pulsating flow. So it's a classical case of a dynamic system. Then these pulses are actually are diminished by using a very large vessel to hold this whatever these pulses are coming, they are stored, are basically are sent into a very large vessel where it will dampen down the flow, and then a steady state flow is being in the outlet. You will get a steady state flow which is sent to the reformer as a fuel. So when you are having a very large volume, the dynamic system become uh, less important, or become a very actually the response is very slow. So equipment, providing the actual equipment sizing, whether it is a a wall, whether it is sorry, the pipe, or the vessel or the column, even for that matter the heat exchanger. So all these equipments will provide some volume, and the volume will tell you how fast or how slow the response is for the given change. So a very important parameter here is to understand that you have to give an equipment sizing also, and it has to be very correct. Otherwise, whatever analysis, dynamic analysis you do has got no meaning. So that is why sometimes the dynamic simulations are done at a later stage where you have already freeze out all the the plot area, etc., the piping, routing, etc., and you have got the final volumes of the equipment, and then you can put all those and to get the meaningful result out of it. So remember to pay attention to the pressure drop across the plant. No pressure drop, no flow, and positive pressure gradient is equal to negative flow. So that means, in when you are carrying out the steady state simulation, there is no chance that it will have a negative flow. While as in the dynamic simulation, it is possible, and it is also reflecting what is happening in the plant. So if the accumulation builds, and if there is no flow, suddenly there is no flow. Obviously, it will the flow can move in the negative direction, or it can show you a negative flow. That means the direction of the flow is in the opposite to what you have assumed initially. So all that can be captured within the dynamic simulation. Now, next is the dynamic pressure and flow specification. So, so the first step in converting any model to dynamic is to add a dynamic pressure or flow specification on each boundary stream. I'll show you where you see all these windows and other things. So we have, if you have done HYSYS dynamic, HYSYS in steady state, so you are aware of this worksheet and attachment. So we will see, that dynamic also now in the this particular session. Add a dynamic pressure or a flow specification on each battery limit. So you have been given the two options, whether you want to specify a pressure or you want to specify a flow. The flow can be molar, mass, standard ideal, or liquid volume. At standard condition. So you have to specify either of these. So these specifications represent how the external world interacts with the process. So whatever node that is considered right now within that dynamic simulation, apart from that, even though it is a part of your entire process, that becomes an external thing to this node. So, to give an example, so feed may come from a storage tank, product may go to another processing unit. Export line may connect to downstream facilities. So, dynamic specification values are generally initialized using so these are some of the examples to name. So you will consider node by node. We will consider the dynamic, and beyond that, it is all external. So that has to be kept in mind. So the dynamic simulation are generally initialized using steady state result. So you first run your steady state simulation for that particular portion. Uh, uh, so uh, and then you have to activate either pressure or flow, not both. So that is the one important thing. So you can see in this screenshot also, the pressure has been activated, which is a more commonly used for dynamic simulation. And then you once you do that, you are you have covered your first step. So again, now why pressure and flow both are are not to be clicked. Because as I said, now that P and F, they are interrelated in dynamic. In when you are doing steady state, you have to specify pressure, flow, composition, temperature. Four specification you have to make. While as in this particular case, when you come to a dynamic, it is the pressure, and then all these the volumes and the resistance and other thing that will tell you how much flow is going to occur. So if you specify pressure and flow both simultaneously, then the it goes actually a wrong signal to the basically a conflicting signal to the software, and it is not able to then able to decide whether we have to see whether the flow is correct or whether the pressure is correct, and then that is not permissible. And then if you see the latest versions of ISIS, it will give you an error before it solves the dynamic simulation. Uh, in pressure node operations, our locations, as we have already discussed, where the material accumulates. So like the vessel, or where appreciable amount of volume is there. So separators, tanks, columns. So these are some of the examples for that. And so unlike pipes or walls, they can accumulate mass and energy. So pipe, even if you consider it's around 5 to 10% of the volume of the vessel, if you consider only the node part of it. So so these are considered as a major impacting volumes, and these are the pressure node operations. In dynamic, this accumulation directly affects the pressure. The relationship that is shown here is delta P by, sorry, dP by dt. So there's a pressure variation as a function of time, and then it is a function of the volume of the equipment, the flow, and the temperature. Um, the temperature basically affects again the volume here. So uh, so it is considered as a separate item here. So this is extremely important because real vessels do not respond instantaneously. As I said that, one classical example which I have given for the PSA. So if the volumes are very high, then the response is very slow, and while when the when you are having a lesser volume, the response is much faster, and the action that needs to be taken also has to be very fast. So this is a very important thing. Uh, this slide explains you the physical principle behind the pressure node. A vessel has a fixed geometry. That means dV by dt is 0. So the physical vessel size does not change. So however, the temperature changes, material inventory changes, and vapor generation changes. So these are all affect the volume of the inventory, not the volume of the vessel itself. And then so that is how, because since we are having a fixed volume of the vessel, and there is a change in this the inventory within that particular node, because of the temperatures and the material, and maybe because of the thermodynamics, maybe the more vapor generation because of the high temperature. So it will exert a pressure into the system. So so the pressure inside the vessel so will depend on the hold up quantity, the vapor liquid equilibrium, enthalpy, and the temperature. So that is how they are related within the pressure node. So the dynamic simulation captures this time-dependent response, and is especially important for the surge drums, flare knockout drums, reactor separators, compressor suction drums, uh, and these units often determine plant stability during disturbances. So this is the important parameter that needs to be kept in mind. Coming to the next point for the pressure node, so the volumetric flow balance can be expressed as a volume change due to the pressure change, plus volume change due to the flow change, plus change due to the temperature change. Basically the compressibility effect. And considering so let's see the example here. So there is an increased flow rate. That is in the feed stream. So the feed stream is uh, uh, so what will happen next? So increase in the flow rate. will increase the liquid inventory within the vessel, because the flow will carry more liquid into the system. Then it will, because of the level, because the level will keep on increasing. And because the level has increased, the vapor space that is there for the for the gas separation, now it has reduced, and because of that the pressure will increase. So pressure will increase in the vessel. Now what will happen now? The pressure can, in a dynamic system, the pressure in this vessel and the pressure that is there in this feed, they may get equal. And in that particular case, the feed from the from that is coming in will automatically will be cut off. Or it may so happen that the vapor, it can go as a high flow from the vapor. So there are multiple scenarios that may happen depending upon what exactly is actually, how the system is going to, whether there is a block thing here in the vapor outlet. So it will, the pressure will equal, and then they will, the feed will be cut off. If if still it will keep on increasing and there is no PSV, so the reversal of flow may also occur. So these are the different scenarios, that the system is going to see. And how the system is designed. Basically, the dynamic simulation can give you how the, whether the different scenarios can, whether the system is adequate from the process, from the, the safety point of view, to handle different scenarios. So two examples which I have already uh, told here. Coming to now the resistance. So the resistance, the pressure and flow relationship, they go, as a flow is a directly proportional to the square root of delta P. Again, now, how what is the occurrence of this? We know that the Bernoulli equation. So if you remember your Bernoulli equation, the pressure and volume. So the velocity is in the, are basically in the square form, right? So if you take velocity as a unity, as a one, then pressure will be in the square root form. So this equation has got a fundamental basis. So in process system, flow encounters resistance due to friction, wall restrictions, pipe losses, equipment internals, and the resistance equation determines how flow changes with the pressure differential. So typical equipment using resistance equation includes heater, cooler, heat exchangers, pumps, compressor, etc., reactors, columns. So wherever the equipments are there, they obviously have a certain effect on the pressure drop. And the pressure drop relations are, can be through an inlet nozzle, through an outlet nozzle, through an internals. So if you are having a tray, so the tray may give some resistance which will to the flow for the mass transfer, and then it will eventually cause the flow to occur. So the conductance terms, often called K here, that is shown here in this equation. So it's calculated using steady state flow, and density and the pressure drop. So how it is calculated, that we will see that in the workshop example. And this is because the hydraulic characteristic, this becomes the hydraulic characteristic basically of the equipment. So we can think this conductance as the ease of flow through the equipment. High conductance means low resistance. Similar to, you can relate it to the electrical resistance. So low resistance, high conductance is actually equivalent to a low resistance and easier flow. On the contrary, if you are having low conductance, that means high resistance provided for the flow and the greater pressure drop. So these equations form the hydraulic backbone of the dynamic simulation. So this is what, so you will see how this K is being calculated for each of those equipments and other things, that when we will talk about the example there. Okay. So again, now the walls. So walls are one of the most important dynamic element. So sometimes when we are developing the steady state simulation, or rather most of the times, we don't give any pressure drops. So vessel separators, we don't give any pressure drops. So in that particular case, we need to add these walls as as the resistant equipment into the system. And once we add, while converting your steady state simulation to dynamic, you will see multiple walls which are not there, but now are the part of your simulation scheme. And those walls are actually are the one which are present, which are providing a resistance to the systems, and which is occurring, because of which the flow is occurring through the system. So in this, the proportionality constant, so which was there in our earlier simulation K, now it is being replaced by the CV. So CV is the one which is, it's a, by definition, it is like, the how much of the liquid that can flow through a certain pressure drop. So that is the definition of, of the CV. So it is exactly fitting the K equation, and it's replacing the K equation from the previous relation that we have seen, which is a generic in nature for all the equipment. While in case of a wall, it is actually K is replaced by the CV. So if the wall opening decreases, resistance increases, pressure drop increases, flow decreases. Similarly, if you see on the, if the wall suddenly closes, the downstream flow rapidly decreases, because we have increased the resistance to the maximum, and because of that, the upstream pressure rises, controller begins reacting. So that is how the walls in the dynamic system they behave. Uh, okay. So equipment sizing inputs now, so again, this is one more important thing. We have to typically the equipment sizing data is available under rating tab, the dynamic tab, and the equipment sizing utilities. So we will go into more detail. So in that, you are having a rating tab, if you have observed any time. So this, in rating tab, you can provide the size of the that particular equipment area itself. So that can add basically to the dynamic simulation. The important include the inputs include the wall sizing, wall type, normal operating position, pressure drop, flow rates, separator dimensions, heat exchanger sizing, heater sizing, etc. So Aspen ICs provide default sizing routing, but engineers can always review that generated values carefully, and then they can modify it. Why? Because again, now the, as I said, that the volume is very important, and the response of the system 100% depends upon the volume that is being considered. And so it is very important that what is the size that you should be, it should be exactly representation of what is there in the plant, so which will give you a more correct result. Uh, Now these are the guidelines for transitioning unit operation to dynamics. We'll go one by one. So boundary streams. So this is, it's a basically a summary. So already we have we have talked about these points in our earlier presentation, but we will summarize, and there are one or two more points that we will cover. So boundary streams, they insert walls or boundary streams where necessary. This creates proper pressure flow relationships. So boundary streams are the one which we should be providing with the walls. So this is the, so basically wall uh, cuts out that particular segment which we want to study under dynamic simulation. So you can see here, there's a wall, and we have to consider what are the battery limit conditions. Uh, Apart from that, pressure specification, yeah, we have to place pressure specification of all boundary streams. So that we have already seen, it has to be either pressure specification or a flow specification. In the distillation column with a condenser requires an extra specification around the condenser. So to make flow specification for the reflux flow. Walls use of pressure flow relationship as the dynamic specification for the wall that we have already discussed. K is basically K value is again a resistance equation, and that is very generic for all the other types apart from walls. The pressure gradient, be sure to account for pressure gradients throughout the flow sheet. Moreover, be sure to specify reasonable pressure drop or rises in the flow sheet. Pressure differential are the driving force for the flow through the process equipment. So this is a very important concept that we have talked many times. Uh, Continuing on that, the tray sizing utility to estimate the column geometry and pressure profile. So if you are working on a column dynamic simulation, so the tray sizing, it's a utility within the HYSYS that can be utilized to represent the actual performance of the column hydraulics within the system, and then you can actually see the performance for the dynamic simulation. The mixers again, they use the equalize all option as the pressure specification for the mixture. The other option, the minimum of two will not work here. So this is a very one important thing that needs to be noted here. In T's, remove use splits as dynamic flow specs or trees. Rotating equipment use efficiency and either head pressure rise or as a dynamic specification for rotary equipment. Compressor and pump curves are very important because like a vessel which is defined by by the dimension, while as in the rotating equipment it is defined by the compressor curves or the pump curves. So it will give you the true representation of what is happening or how the system will perform for those rotating equipment. Hold up, be sure to properly size equipment with holders. So dynamic simulation can only be modified when the integrator is stopped. So what is integrator? That we have already seen. Integrator is nothing but it with respect to time. So it will it calculates the changes for that particular node with respect to time. So once you know that all the integrator is stopped, that means the calculations are done, then only you can modify the dynamic specification. You cannot make any modification while that integrator is on. It will not, that software will not allow you. So this is one important thing uh, that needs to be remembered. uh, Solving strategy. So HYSYS dynamic uses a simultaneous equation solver. This is very different from steady state sequential solver. In steady state, units solve one after another, which we have already talked about. The entire flow sheet equation solve but in dynamic we normally solve the entire flow sheet equation simultaneously. So this becomes necessary because pressure interaction occurs everywhere. Flow changes affect multiple units simultaneously. Controller interacts continuously. So whatever node that we have considered, so the things are happening, and it's a function of time. So it occurs at the simultaneously at all the places. So the solver also internally solves these equation for all the all the entire for the entire system under consideration um, uh, 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 at a same time. And degrees of freedom analysis is used to verify whether the model has sufficient specification. However, degrees of freedom satisfaction alone does not guarantee the correct modeling. So this is also important point. You may still require physically inconsistent specification, unrealistic hydraulic behavior, improper pressure relationship. So all these may still happen even if the degrees of freedom analysis is correct or in place. So therefore, we must combine. the mathematical correctness, physical engineering understanding, and so this is very important. And that is why the dynamic simulation requires a certain feel of the system or the plant. So if a person who has seen the plant and who knows the dynamic of the plant, and if he does the dynamic simulation, it will be more practical. I'm not saying it will be correct or incorrect, but I will say he will try to visualize the things more as compared to a new person who has not seen the plant. So it is better that once you do these dynamic simulation, try to see if the basic principles that the plant sees are actually, if you are not seen, you can confirm it from a senior person who has done that. So it is very important. It is not the steady state simulation; it is the dynamic simulation. So even if you do the dynamic simulation, you have to see the correctness whether it is following. It is the same principles are being followed in the plant also. To give you an example of degrees of freedom, so this is one example. So seven variables will define the system here. Now the pressure and flow of the feed one, product one, and product two. Okay, so these are basically pressure flow, and pressure flow. So six variables are there. Separator pressure, so that is one, and then there are four equations define the flow sheet. Uh, so, uh, so the turbulent flow equation, uh, the F for the wall is directly proportional to the pressure drop. Separator dP by dt is function of VFT, which is for the separator, and then the degrees of freedom are basically three. So you have to specify three variables which will completely define the system. So that is how, like the same analysis that we do normally with a column. So when you are having a steady state simulation, when you are having an absorber column, you see the degrees of freedom. There is no degrees of freedom. So once you define the two streams, it will automatically calculate. But when you add, more equipments into that, the degrees of freedom increases. So same principle is here applied to this also. So for this simple node also, you can the example is given with the seven variables. The variables have been provided in red, and then what are the different equations that we are talking about? So there are three walls, so having a three equations, resistance equation and one separator equation for the accumulation. And once we have, so then that means if you define the three variables here within the system, that will give you how the system is going to perform. So what no degrees of freedom that we are going to tell is the pressure and pressure. So if you define these three, and it will give you the uh, it will start solving the equation. Now, so these include basically, as I told, the pressure specification on the material spring, flow specification on material spring. So either you can specify pressure or flow, then fixed pressure drop across the equipment pressure flow, and pressure flow equation calculated for walls, and conductance calculator for process equipment. So acceptable solution is most of the time we normally go with the pressure specification, and consistent solution is vessel pressure calculated by hold up equation, steam pressure calculated by resistance equation. So that is an acceptable solution for most of the cases. So that has to be kept in mind. So I hope this is clear, or I'll just again I will just repeat it, so that you will have again the same understanding. You will have the same understanding, because this is a very important concept. So we are talking about the seven variables here: pressure flow, and the pressure in the separator. Okay, so this is very clear, right? So if you count, there are total seven variables in this. So all pressure flow. So 3 into 2, 6 plus 1, 7. There are four equations. The four equations are out of that, three equations are for the walls, So there's a resistance equations for the three walls, which is represented by flow is directly proportional to square root of pressure drop. Then you are having an accumulation equation for the separator, which is a dp by dt as a function of volume, flow, and temperature. So if you negate it, the number of equations minus number of the number of variable minus number of equation, which gives you the degrees of freedom. So that means you require three variables to be defined, which will define the system and it will run the dynamic simulation. Now, what are the variety of specification that can be made? Pressure, flow, pressure, flow, pressure, flow, and pressure, right? So the pressure specification on the material, flow specification on the material, streams, fixed pressure drop across the equipment, pressure flow equation, that means the wall, or the conductance equation, a calculator for process equipment. So, what is the best practice, or what is the best practice that is used or recommended is pressure specification for all the three battery limit, and consistent solution is either by vessel pressure calculation calculated by hold up equation, and steam pressure calculated by the resistance equation. Okay, so it's clear, right? So the guideline or the rule of thumb is uh, so uh, uh, first rule is one pressure or flow specification per boundary stream. Avoid pressure or flow specification on internal streams. Uh, why? Because internal flow should develop naturally based on the pressure gradients, right? Then rule number three, pressure specifications are generally preferred. Add walls near separator and boundary streams. Rule number five is internal flow rate should be pressure driven. This philosophy mimics the real operating scenario, uh, and then so these are the five golden rules which are mentioned here and should be followed as a general practice. Uh, if you in case if you don't remember, if you are doing it for the first time as a practice, maybe you are not used to all that. So don't worry about that. In a HYSYS we have a dynamic assistant. Okay, so this dynamic assistant is a tool which will tell you what mistake you have made when you are converting from a steady state to a dynamic. So what mistake you have made, and then it will tell you one by one what changes it has to be made. It will do it automatically, and if it doesn't, you can actually choose it and make changes. So make changes button is there, so you can make changes, and then automatically all the has been taken care by the system itself, and then you can proceed with the dynamic mode. But before you give it to computer all control software, you can have a look at it and just make a you can verify that with whatever rules that we have specified in our previous slide. So five golden rule that needs to be followed. If it is lying in those within those rule book, if it is okay, then you can just make all changes. So it is helping you basically. So if you have miss on any of these rules, okay. Uh, so uh, so dynamic PF and color scheme are like this. So if you uh, 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 so the so this is the color that is color that is being used for the dynamic simulation, and this also helps you basically to when you are developing a dynamic simulation. So this is the second way how you can verify whether you have correctly specified your dynamic simulation. So there is a dynamic PF and spec here within that default color scheme. Those, so in when you are carrying out the simulation, you will have a default color scheme. Instead of that, you can go with a dynamic PF and scheme, and I'll explain you what is the meaning of each of those colors in our example. So you make pressure changes on all boundary limits, add walls to boundary limit, size process equipment, enable PF and equations, specify C's and K's, and say, and then you are ready to go with the dynamic. So let us, uh, start with the workshop here. Uh, I'll just open my HYSYS. So this is the steady state simulation that we have carried out. Okay, so you have done a steady state simulation. So it is not a very very complicated simulation model. So we are having a three basically. Just let us open it. So you can see there are three streams that are coming from three different wellheads. Alpha, let's give a name, Alpha, Bravo, and Charlie. Then it is transferred from through a pipeline, and then there is a wall, and then they are all mixed together. So the three wells, offshore wells or onshore wells, they are the fluid is being transported to and mixed before it goes into the separator. So this separator is nothing but like the slug catcher or the first separator that is it is going to see this. And the vapor that is now which is coming out, it is now then it is cooled, and then it goes subsequently to the next system. So this is the actual representation of the steady state model. The model is cut till the separator part and the exchanger part. Okay, so this is how the steady state simulation looks like. Okay, so what we are going to do is we are going to do following tasks. One is that the equipment sizing, the define pressure and flow specification, and then move to the dynamic mode. So these are the three steps that we are going to what we have already discussed in our presentation. The same we are going to demonstrate in this particular workshop. So in this workshop, the objective is to convert a simple steady state model to a dynamic in Aspenices. We'll provide equipment sizes, dynamic specification in the simulation, and then we will illustrate the fundamental concept of Aspenices dynamic, which will later be expanded into model to include detailed equipment performance and the rating capabilities. So let us go with the first task, which is equipment sizing. So the dynamic model to run and calculate properly, many inputs are needed and to be formatted differently than they are in the steady state. So some items that must be added to your model while others need to be removed. So in general, following items are required. So add some unit operation as necessary, size your equipment, adjust pressure specification of column model, address remove logical operations, add control operations, all that are not required, which you have used in your steady state simulation. So you can remove basically some of them, or you can add some of the unit operation which are relevant to your dynamic simulation. So let us do the sizing. The first important thing is the sizing of the equipment which are there within this. So what are those equipment? Pipes, yes. Pipe, I have volumes, so pipe is important. Walls, yes, we have to do the sizing of those walls. Mixer, there was one important thing that we have talked, we will see what that point is. And then exchangers and the separators, right? So we will go with the walls here. Let us open this one of the walls. So the sizing, you can see here the rating. So rating means we have to do the sizing for this. Sizing for the wall is nothing but estimating the CEV value. So that inlet pressure has been taken from the current. So it has, we have run the steady state simulation. So that is why you can actually choose so once you put a current here, radio button, that means it will automatically take all the information which are there. So you can see here the 6982 is there. So you can it is taking that flow into that. So wall opening is 50%. So normally, whenever the control wall is there, it is normally for the better controllability, the wall opening is normally designed at 50%, and then it can actually go up and go down. and it can do the adjustment. So no, normally 50%, again, this is a very, I'll say the default number that comes with the HYSYS. Uh, then I am going with the different, the manufacturing specific methods. So there are, the wall characteristic. You can see the linear, quick opening, equal percentage, which are available in the market. I'm choosing linear here, and I am, choosing the manufacturer specific method. So you have an ANSI method, then you have a manufacturer specific method. So I'm considering here the universal gas sizing, and then I'm just push this size wall. So it will give me, the size, which is a CV for that. Okay, so this is the value that we will get finally. Similarly, you can do the sizing for all the walls. So again, now I'm doing the same thing. So I have already done that. So you can go into universal sizing, rating more, and then do the size wall, and it will calculate. So same way you have to do it for all the walls which are there within the battery limit. Basically, not just for wall, for all the equipments. So I have done it for all the four walls and size wall. Okay. So this has size all the walls uh, within my node which I am considering. Now the next is basically I can see here the HP separator. So in HP separator I can put some volume here. Again, now if you can see here, so this is the normal thing that you are aware of. If you go into the rating, you can see whether that vertical, whether the vessel is vertical or it is a horizontal, flat, cylinder, sphere, ellipsoidal head. All information is provided to you. Options are provided to you. You can add, the things here, and it will automatically calculate the diameter and the height based on the thing. So I have already given the volume here. The next thing is basically, giving it for the cooler. So which is the next equipment. So if I open this cooler, again now into the dynamics, you can see here there is a volume. So you can, because again the volume is very important in this particular case. You have to give the volume here. Um, uh, so volume I have already given. So I have given all the uh, in pipe segments. Again, the pipe segments, I think from steady state simulation also we do. When we do a hydraulic calculation, we normally give all this length, etc., diameter, etc. So the piping volume is available within that. So you can see here the length is around 1000 meter. Elevation change I have not considered. Outlet and inner diameter I have checked from the schedule number. So the same thing I can do it for all the pipings. So in this case, I have given volume to the pipes, the separators, separator, the exchanger, and I have given a resistance equation for all the four walls. Okay, so that means I have sized these walls. Okay. Now, if I go into the just a minute. If I go into flow sheet, I can see here, the Hycene color scheme or dynamic PF scheme. So you can see here, there are red, there's a blue, and there is a green. Okay, and again you can see here the blue and the green. So the blue stream represents no dynamic specification. That means I have to do dynamic specification for the blue color. When green is there, green is basically the dynamic pressure specification. So you can see in this, the dynamic pressure specification has been provided. Then yellow stream is not there, but there is again a yellow stream is there when you make a specification for the flow. So I think if you go into this and then if you make a flow specification, it will turn into blue, yellow. Okay. So yellow is for basically for a dynamic flow specification. Red stream is where it's an error. That means it's a bigger error. That means you have specified both pressure and flow specification, and gray is basically for the energy streams. Okay, so so this helps you basically. Color scheme helps you while specifying all these. So we'll check into the will make all these corrections here. So if I go into the alpha and if I go into the dynamics, okay, so dynamics I can see here it is a red. That means both pressure and flow are both are active. So I will just remove the flow. It is only now a pressure. Now it has, suddenly it has now from red it has changed to green. So same way I will do it for others. Okay, and again Charlie. Charlie also dynamics and uh, pressure. Okay, so I have made these changes on the pressure specification at the outlet at the inlet, and that means it is now it is green. Same way you can see here, the another rule that we have iterated, that within the system it should not have any specification. So this green is not correct. So we have to go there and we have to remove that. So then all are blue basically. Okay, so this is now a correct thing that is there. Okay, okay. One more thing is the resistance or the K equation that we are talking about. So we have to we know the resistance equation for the wall, control wall. So the control wall is basically the CV. Whereas in this particular equipment, this also, it causes a pressure drop. So we have to have a, a K value calculation. So what we can do is basically you can, the calculate K value has been already calculated. We just have to, if it is not calculated, just click on this button and it will calculate the K value, and then select the, the K value here. So that gives you the resistance equation for the exchanger as well. Um, one more thing I can, I think we have to go and do that. The thing is that the pressure flow relation that you have to click here, it is mostly it will be clicked automatically by the software. But if it is not, just before you start the dynamic simulation, it is recommended to click on the pressure flow relation, that is PF relation, and then you can put a check wall so that prevents the backflow. So once you put a check wall there, so you can see now the reverse flow will not happen through this wall. So same way you can just you can go into the dynamics and then you can use a check wall to prevent any backflow. So if that arrangement is there in your system, do that. Otherwise, you keep it like that, and then you can if the reverse flow happens, it is actually also an indication that you need to have a check wall. So that is one thing. Okay, in dynamics, I'm assuming that all my control walls are check walls, and it is there are check walls, and the reverse flow may not happen. So I have click on that part. Okay, so if you go into pipe, just let me check dynamics. The simple pipe friction model has been assumed. So simple pipe friction model is, again, it follows the the K relationship, resistance relationship. But if you want to use a pipe model correction, you can also use this pipe model correction, which is there. So these bugs, bigs and brill and all those correlations which are used to calculate the pressure drop are being they are can be utilized here in the dynamic simulation. In my case, I am not going. I'm just as an example. I'm going with the simple pipe friction model at this moment. But you can always keep the pipe model correlation, which is being already being chosen during the steady state simulation. You can use that. Okay, once this is done, then we will go to the dynamic mode. So there's a dynamic here. You can see the tab. The dynamic assistant, which we have talked about, an integrator. So the integrator you can see here. the how the what are the time steps, and at what interval you want to do the integration and other things. So all that is specified here, and we will talk about it when in more detail when it comes to the actual dynamic simulation analysis. But this is where you do all the integrator settings. Then for the dynamic assistant, you can as I said that if you miss on that, better to check through a dynamic assistant, and which will give you if you have made the system, or even if you have done everything correctly, and still you can check it through the dynamic assistant whether you have done everything okay. And then if any changes has to be made, you ask it to make the change, and then the it is now uh, uh, ready to go. So once this is done, you are ready to go for the steady state simulation. Another thing is that yeah, yes. So once you say yes, so now you are in the dynamic mode. So now you cannot make any changes as such in the steady state. If you want to go into steady state, go to steady state and do that. So now you can see here, the run and stop button uh, is now active. So the if you start run, it will start running for the uh, as a function of time, it will start showing you all the things. Now another thing that which needs to be seen here is the data logger. So if you go into the data logger, so it is it's a similar to your DCS screen. Sorry, it is similar to your DCS screen, and you can see like your like a DCS screen. You can, once you start the simulation, it will the parameter which you want to see, that can be actually added here, and then you can run the simulation and it will be seen to you. So data log, okay, display, and then you start the run. And then you can see here the integrated running, the current time is 00. So it will start running your dynamic simulation. And then yeah. So you can see here now the time scale is changing, and as the time changes, you will see the plots which are which in which you are interested. So I think that can be will be done at a so when we will take some actual problems. So with this we have demonstrated the how we can convert a steady state simulation into a dynamic simulation, and then we can see the how the the parameter that you are interested, maybe a pressure, maybe a flow, can how it can vary as a function of time. So when you disturb it, it will then you can see all those disturbances in those display. And then so I have stopped right now. So all that can be seen here. So this is a very basic, or I'll say the first step. I'll say the first step or the basic steps that irrespective of whatever the simulation that you are doing. So these are the basic steps that needs to be followed for for converting a steady state simulation into a dynamic simulation. So with this, we have come to an end of today's webinar. So today we have discussed the fundamentals of dynamic simulation, difference between steady state and dynamics, pressure nodes. What are the pressure nodes? Basically, hold up hold up volume becomes a pressure node. Resistance equation, equipment sizing, that is very important in this case. If it is a basically a static vessel, then the equipment sizes are important. When it comes to pumps and compressor, the The charts, the characteristic curves are important. When it comes to wall, it is the CV value is important, and in the heat exchanger, it is the the volume of the heat exchanger, and the heat transfer area is also one important parameter. So the heat transfer area is UA is becomes a constant, and as you change the flow accordingly, the UA remains same, but then the other two streams they get reflected. So we know the characteristic of each of those equation equipment. So those becomes very important to be specified under dynamic simulation. Then uh, so, uh, one important another important parameter is the pressure flow relationship. So, pressure drop will create the flow in the system, and either you specify pressure or flow at the battery limit, and then you can see the effect of the disturbance of those parameters onto the entire system. Mostly, the pressure is the one which is chosen for majority of the system. Transition methodology in Aspen HYSYS, that also we have seen what are the things that needs to be done. So dynamic simulation becomes is becoming increasingly important in modern industry due to higher safety requirement, complex control system, startup shutdown optimization, hydrogen LNG applications, digital twin development, operator training systems. uh, so, uh, so I encourage all participants to practice these concepts using small models initially before moving towards large integrated system. So to have a feel and then how the dynamic system work, and then you will be will be able to judge whether the system is responding, because the dynamic system it is very difficult. They will run steady state simulation. If the basic principle is violated, they will not run. But in dynamic simulation, normally, it will give you some results. Now, whether those are results are meaningful or not, so those you have to make a judgment of your own, or you can go to a experienced person who can help you in understanding whether that whether the actual system also work in the same manner. So that's a very important thing. You can build your confidence by doing all these small models, and then you can go for a large integrated system. Thank you all for your participation and attention. So if you are having any questions, we can discuss that.
Yeah, we request everyone if they have any questions, they can add in the chat box.
So again, now this is a very basic. I think this is just like chapter one. So we have covered what in that presentation. So the overall coverage which was shown here. So we have covered only the three part of it. So the what is dynamic simulation, how steady to versus dynamic, and basic concept of accumulation, how everything. So that we have covered all these three parts. But when it comes to the real system, when it comes to the training of the dynamic system, so then we will be going either with the control systems and compressor anti-surge systems. So these are the two popular things that normally are taken when it comes to training part.
We have some questions in the chat box, sir.
Yeah. Just a minute. I am not able to see any question here. Okay. Can we convert dynamic simulation back to steady state? No, no. Actually, see, You can convert, but problem happens is when the dynamic simulation runs, for a time, so it will, it will keep that values in the memory. You can do the reset button, but then you have to make ensure that it has come back to a steady state simulation. But the good practice is, you keep the steady state simulation as a, as a backup file, and then you run the dynamic simulation. You can definitely, you can come back to the steady state simulation for simple system, but for, for complex system, as you move, as you do a more complex system, some of the values, they remain within the, within the memory of, the simulation. Okay. So it is always better to keep your steady state simulation as a backup file and then run on. So you can see here, in my system also, I have prepared three, four files at different levels. So the first steady state simulation is there. Then I have, done some changes and I have saved it. I have made, ready for dynamic. You can see all that, So these are basically, to just to keep the, the original file with you as it is, and then you can always, so that is the practice. Dynamic simulation can definitely be done in Aspen Plus. It also follows the same thing, same principle. The Aspen Plus also follows the same principle, exactly what, the Aspen HYSYS follows. Only thing is that, the basically, how the Aspen Plus, even for the steady state, it runs slightly different than Aspen HYSYS. In Aspen Plus, you have to develop entire model. It will not solve by itself. Then you have to give a command, and then it will solve, all the unit operations one by one. So that is the only difference. But apart from that, the principles are exactly the same whether you use Aspen HYSYS or Aspen Plus. You mentioned Olga in the beginning. I was under the impression it was a pipeline simulation tool. Yeah, correct. Yeah, yes. Actually, Olga has got two, flow assurance studies. One that is done by Olga. Another is, the dynamic simulation. So it's a, Olga dynamic is also there. So that is used only for the transient analysis of, the offshore pipelines or the big pipelines. Even if it is onshore, if the big pipelines are there, the transient analysis is done by Olga, and which is much more reliable and correct as compared to any other software. Olga is basically designed to do that part, but it is only limited to the pipeline. And HYSYS has got a capability where you integrate Olga into a process equipment, which is HYSYS. In HYSYS itself, you can see, there's a, I'll just show rather than talking all that. I can just show that. Uh, just a minute. Function F4. So in pressure pipeline and hydraulics, you can see here the Volga, the pipe seam, the pipe seam net unit. So all these, Olga pipe seam and other things, they are the, this is where you can actually, integrate your, these pipelines. No? You can do the transient analysis using Olga. Okay. And the Olga output can directly be, if your organization is having a license for Olga as well as HYSYS, you can extract your Olga transient analysis directly into HYSYS using the connector, and from there you can do your downstream dynamic simulation using HYSYS, because Olga doesn't have the capability to do any transient analysis for the downstream processing. So Olga and the pipe seam, they help you to do the transient analysis for the pipeline, and then you can integrate, because a lot of people, and it's true also that Olga and pipe seam are much better software for the pipeline simulation transient analysis as compared to HYSYS. Uh, Aspen ISIS model intent for cause and effect metric analysis. Yeah, definitely. So that is yeah, that is important. I'll say aspect of doing the dynamic simulation. So once you have freeze your detail engineering design, you can put all those details node wise, and you can do the cause and effect analysis. So high flow, no flow, and other things. Even the you know the study, the HAZOP study also can be quantified using Aspen Dynamics. You can also do the cause and effect analysis as well. Definitely, you can do that. Can we run dynamic model in CameCAD because we have CameCAD now? Okay, CameCAD I have never used earlier. Uh, I don't know because I think CameCAD is mostly, as per my understanding or knowledge, CameCAD is mainly developed for the chemical processes, and it is mostly for the for the steady state simulation. I'm not aware of the dynamic model whether we can do that in CameCAD. Sorry for that. Can we use this for ETP operation? Yes, definitely. Not an issue. Dynamic simulation is least bothered about the systems. Rather, what how many details are important. So if the details are available, you can definitely use that for ETP operation as well. Any other question? If I have left anything, sir, can we do revamp and troubleshooting in dynamic simulation? Yes, revamp definitely for the control system. You are having, in revamp, you are having most of the things which are existing and the details are available with you. So you can add those things in your dynamic simulation. Troubleshooting again, definitely for the dynamics. Again, steady state and dynamic, the outputs are well known. So in dynamic simulation, you want to see how the things like it is an OTS. So you give the scenario, and then it will actually, do the it will give you an output basically. Yes, revamp and troubleshooting, they are the perfect scenarios basically. So you should have the enough information available with you to put into the dynamic, and then it can give you much more inside of what is happening inside the system, and it can help you basically in doing troubleshooting. Or any other questions? Have I missed anything? Uh, Thank you for your remark. Real-time text in Microsoft Teams stayed visible throughout the session, which become distracting. Okay, we will take care of that next time. Thank you. You mentioned Olga in the beginning. I was under the impression. Okay. Any other question? I think I have. We have covered. I think whatever questions which are there. What are the key considerations and precautions? Considerations and precaution, again, the dynamic simulation, you have to follow a certain procedure. So this is the basic procedure that you want. Apart from that, as I say, that the volumes, the resistance equations, you give as much as the realistic information into the system, into the for the dynamic simulation, more correct results you will get. That is the most important step that I will tell. Steady state is basically a conceptual one, where you, even if you are not having many of the information, still the thermodynamics, material energy balance principles will tell you what is coming in, what is going out. But dynamic is not like that. Dynamic requires very specific information, very detailed information, and that has to be provided. Once you give that, and if you follow the basic principle, five principle that we have mentioned in this PPT, I think that will be good enough to start with, and then you can also verify, whether the basic principles have been covered, or the trends are in the same direction. So at least it will give you some direction why what is happening. Maybe the quantification may not be exactly correct, but at least it will give you a directional, uh, information that why this is happening, why how this is happening. Okay, so that definitely it will help you with if you follow the basic principles of dynamics. First year student, I think you have to learn first chemical engineering for next 2 3 years at least. At least you should be 3 years or 4 year. Third year, if you have completed third year at least or fourth year, because the dynamic simulation requires uh, a process control analysis. So at least the process control subject should have been taught to you. So once that is done, then you can actually think about dynamic simulation. So that is my advice. Uh, Start of the session about advanced process control. So what role it plays in dynamic simulation? Okay, so advanced process control. So you have got basic control system. So if you want to control the level of a separator, so the levels controller will have a level control wall at the outlet of the vessel downstream, and that is connected to the level. So if the level increases, the wall will proportionately open, and that will reduce the level of the level in the vessel. So that is a very basic process control. Similarly, there could be some cascade control also. There could be a ratio control also. So the flow and level can be can also be interrelated. So when you go to a bigger picture, so in a plant you have a multiple process control that are happening, and some of them are interrelated. So when you go nowadays, people are going with the advanced process control. So what it does is it has a certain a process control which is sitting above the normal regular process control, which is there for the process safety or the safe operation. Okay, so this safe operation now it has been programmed in such a way, because like what you do for the steady state simulation, you come to an a minimum energy consumption scenario where if you operate the plant, if you say maybe a steady state plant, if you integrate this way, it will consume the least energy. Same way, if you operate a plant a certain way, it will give you a least energy. So if you have to operate the plant in a certain way, so the dynamic system comes into picture. So this dynamic is basically controlled at an apex level by using an advanced process control. So that will tell you how much it's an basically it sits above all the process controls, and it will try to keep those process control in place so that you will get the best output under the dynamic simulation from the real plant. So that is the concept of APC, and it has been used in the form of a digital twin. Like what Jatin has mentioned in the at the beginning of the presentation. So the digital twin is one concept where you take all these control into picture, and then you see what is the objective, whether you want an energy objective or if you are having a maximum production. So you set those production or the energy objectives into the give to APC, and it will rather than the operator, the APC will start giving command to the process control that operate now, since this is happening, you should operate this way. So there is no delay in the operation, the response to the to these fluctuation, and the plant is smoothly run at its best point. So that is the idea of having APC. Still, I'll say people are claiming advanced the digital twin, but we are still away. It is not that it has fully taken over. APC has taken over the project plant. We are still away, but yes, we are maybe I'll say 45-50% near to what we are seeing at this moment through APC. Uh, any other? Yes, PipeNet transition flow analysis data can be exported to Aspen and it can be integrated with the dynamic simulation of the Aspen to see what is the effect in the downstream equipment. Yeah, it's possible. Yeah, there are these whatever I have shown now that those are called connectors. So if you are having both the licenses, Olga or PipeNet and ISIS, you can integrate that. Yes. Okay. So best of luck to all of you, and thank you for attending the session.
Yep.
Uh,
Thank you.
yeah,
Thank you everyone for joining today's webinar. We truly appreciate your participation. And we also thank our trainer, today's trainer, for providing us with the valuable insights on dynamic and steady state simulations, the thumb rules, and practically industry applications. So, looking forward to connect with you in our upcoming workshops or webinars. Please keep us following. We will come up with another topic in another month, and we have shared the feedback form. So please fill the feedback form. We shall share the presentations to those who have filled the feedback form, and appreciate your feedback for today's webinar. Yeah, thanking you all. Thanks, our trainer, and have a great Sunday. Thank you.
thank you,
Thank you. So, thank you.
thank you, thank you.